So, what's up, everybody? Welcome back to another exciting week of Proof Set Theory and Logic. Let's do it. So, one thing first, I will send an announcement about this as well, but class on Friday, canceled. Not going to happen. There's a conference that we're hosting here. We got some money from the NSF to bring a bunch of math people here to talk about optimization, and I'm going to referee one of the sessions in the morning. So I got to cancel it for that. Yeah, cool. If you are interested in optimization, I do encourage you to attend. It's free. If you want to hear about a bunch of cool optimization-related topics, just over in the Union. It'll be fun. But yeah, so today we're getting into composition of functions. So section 5.3, bad marker. All right. So we're going to return to our initial motivation, one of these questions we asked before. So here's the idea of how this all works. Okay. If you've got a set, let's call it x, a set, let's call it y, and a set, let's call it z, and you've got some function f that goes from x to y, and some function g that goes from y to z. Let's put some stuff in here. A, B, C, 1, 2, 3, 4, and w, little x, little y, little z. Then we can make a new function. So if f goes like, I don't know, why not make it like this? There we go. If that's f, and g does something like, say, I don't know, like that, okay, then there is this intrinsic kind of a new function you obtain just by following arrows. There we go, that's the good marker. That is, you could go, actually I'll use a fun color like purple. That is, you could go right from x to z just by following the arrows. So since you could go to 2 and then over to y, you could just go straight across to y. And since you could go from b to 4 to x, you could just go straight across to x. And since you go from c to 1 to w, you could just go straight across to w. Now maybe that looks complicated since we've drawn a lot of lines on top of each other, but the whole idea of it is that there's this secret function kind of hidden here that you can take, that you can make by taking two functions and hooking them together by just following arrows, following paths. Okay, pretty reasonable. And so we tend to write this function. So if maybe it's actually going to be a little easier if I write it like this. So if x gets sent to y, make that y look a little more normal, and y gets sent to z, so this one is sent by f, this one's sent by g, then there's this way to kind of complete this triangle here, which is do f and then do g afterwards. Now how we tend to write this is we write it as g composed with f, since we write functions as like f of x, and if we do g on the outside, it looks like this, yeah? Some people will adopt the convention of writing, instead, they'll go f composed with g to mean this, but I find that much more confusing since the order gets flipped around, yeah? So we'll use the convention that g circle f means do g to the result of f. Cool? Okay. But does this kind of idea make sense of how you could go from one thing to the next and then one further? Yeah, I think so. Everyone can follow instructions, can use Google Maps, right? It's the same exact type of thing. I mean, whether or not we can use Google Maps all that well is anyone's guess, right? I get lost all the time. But so the questions become, hey, when you form this new function, this new one you get by following arrows, what sorts of properties does it inherit from the functions f and g? I think we can kind of discern a few of them right away. For instance, if, say, Oh, let's think of an example here really quick that might look a little bit easier. Here. Get rid of all these arrows here. Make a nice new little diagram here. Okay, so here's x, here's y, here is z, and let's say we have like A, B, C, D, and just here I have like a 1, 2, and a 3. Now, if, for instance, G does something like this, is there any possibility for the function G composed with f to be surjective no matter what f is? What does surjectivity mean? It means that everything in the codomain gets hit by an arrow, right? By at least one. Could be more than one, but by at least one. Now, if G doesn't hit everything in Z, there's no chance that the composition would be surjective either, no matter what the first part is, right? It's not like I'm going to be able to get new stuff out somehow, right? Everything I get out is stuff that comes out of G, yeah? After all, I'm plugging things into G, if you want to think of it from the kind of mechanistic way of like functions being little machines to take stuff and turn it into other stuff. But if you just look at the arrows, if you're just following arrows, there's no arrow that gets you to 3, right? It doesn't matter what the first part is. The second part doesn't let you get to 3. You won't be able to get there. Okay, so if the second function, G here, is not surjective, there's no chance for the composition to be surjective, right? What about injectivity? Do we need G to be injective? Let's think about it real quick. What if, for instance, here I just have a, I don't know, star and a picture of a square. There we go. Could you come up with a function so that the result is injective? I mean, G clearly is not injective. 3 different things point at 2. But could you come up with a possible function such that the result of composing f and g together is injective? I see some people nodding their heads and saying, yeah. Okay, let's send, I don't know, let's send the square to C. Well, if I follow it across, that gets me to 2. So all I have to do is make sure that star doesn't get sent to something that maps to 2. If star gets sent, say, to B, then the resulting function just looks like this. I've got star. I can draw a star, and I've got a square. And then I've got 1, 2, 3. And star gets mapped over to 1. And square gets mapped over to 2. That's about as injective as can be, right? Okay, so we have the possibility to get an injective function when the second function is not injective. But notice the first one definitely is, right? Let's see if we have perhaps some sort of a property like that there. That is, if we erase our G thing here and switch up what's going on here, maybe I put a circle in there as well. If this gets pointed at C, certainly f is now no longer injective. Is there any choice of function g that would make the result, g composed with f, injective? What would you do? Yeah, okay, there we go, right on. Someone said yeah, but then we thought about it where we said maybe not. Namely, square and circle are both getting sent to C, right? Now, there's no way, no function type way, to send C to 2 different things, right? That is, I can only have one arrow coming out of C if this is going to be a function. And what that tells us is that no matter what the heck C gets pointed at, which has to point at something if it's going to be a function, then these guys are going to send f is going to send 2 different things to C, and then G will send those things to something else. And so those 2 things will get sent to the same thing, right? So if the first function is not injective, there's no hope that the composition can be injective, right? Oh, okay. So injectivity and surjectivity, seem like they have something to do with the injectivity and surjectivity of a composition, that is, in both directions to some extent. If you have an injective composition of functions, then you know that the first thing must be injective as well. And if you have a surjective composition of functions, you know that the second thing has to be surjective. Yeah? Okay. So yet again, they're kind of counterparts. They have this nice sort of balance between them. So let's prove a few results about this and kind of keep in mind that the ultimate sort of question that we want to get to is when can we reverse the direction of arrows in a function and get back to where we started? That is, if instead we had something like star, square, circle, and I try to reverse the direction of the arrows, well then notice I would end up going like this, and that is no longer a function, right? Okay, so here I can't reverse the direction of the arrows and get a function, but when can I? When can I do this? When can I get back to where I started in some sort of a nice way? Yeah, so we got these injectivity and surjectivity results. Let's go through and finally prove this stuff, this initial motivation about right invertibility and left invertibility. When can you flip the direction of the arrows and have it not matter? All that kind of business. But let's start out with some of these simple observations about compositions and injectivity and surjectivity. So here's a theorem. Actually, first, let me throw a definition at you so we're super clear about what we're talking about. So let's let f from x to y and g from y to z be functions. The composition of f and g, denoted g circle f, which is a function, to be clear, from x to z, is the function g composed with f of x is equal to g of f of x. That is, as a set of ordered pairs, we have g composed with f. Well, this is the set of all ordered pairs. I'll write it as little x, little z, such that, well, what do I need? Okay, so we need some x, y in f, and there has to be some y, z in g. Yeah? Does that sound reasonable? Even better, perhaps, if you like this way of writing it more, since that perhaps looks strange. Let's write it like this. Let's write it like there exists y, little y, in big Y, in like the hidden middle part, such that the following predicate is true. Little x, which is set, y, is in f, and y, z is in g. So that's the predicate that you would be following. It says, hey, there's some middle connector piece so that f takes us from x to that connector piece, and g takes us from that connector piece to the desired final result. Okay, cool. So it's just like hooking them up together. Nice. Okay, so we've got compositions of functions. Now let's prove a fact about them. like we said we would. Theorem. Let f be a function from x to y, and g be a function from y to z. Then we have the following. 1, if f and g are injective, so is g composed with f. And 2, if f and g are surjective, so is g composed with f. Okay, I would say that these are perhaps even a weaker version of what we were talking about before. After all we're saying is that if both of them are injective, then so is the composition. And if both of them are surjective, then so is the composition. We can probably actually do better than this. So let's at least get used to talking about proofs like this first, though. So a quick proof. Let me switch the camera here. Okay, quick proof. Let's try to go through it quick. What would you do? So let's first do part 1. Assume f and g are both injective. Okay. Let x1 and let me make that x a little bit. x2, make these x's look a little bit nicer. In fact, I'll write it this way. Let x1 and x2 be elements of x with x1 not equal to x2, i.e. take 2 distinct elements of x. Yeah? Since f is injective, f of x1 is not equal to f of x2. Do you agree with this? Yeah? Remember, injective says that f of a equals f of b implies that a equals b, right? Another way of writing this as the contrapositive would be a not equal to b implies f of a not equal to f of b. That's the contrapositive, right? Okay, cool, logically equivalent. Okay, now, since g is injective, g of f of x1 is not equal to g of f of x2. Since these two are not equal, these two are not equal, exact same reasoning, contrapositive of the definition of injective, yeah? Okay, cool. Hence, g composed with f is injective. That is, through this chain of reasoning, we've said, look, if you have 2 elements of x that are not equal, then g of f of those elements are also not equal. Yeah? It never sends distinct things to the same thing. Reasonable? Sweet, okay. So what about part 2? Well, let's assume f and g are surjective. We're not assuming they're injective this time. That is, we're dispensing with our observation from the first part, and we're instead now proceeding brand new for number 2. Assume that they're surjective. Okay. Now, let's take z in big Z. Since g is surjective, there exists some y in big Y such that g of little y is equal to z. Yeah? Surjective means you hit everything, yeah? So surjective says for all, I'll write it this way, z in big Z, there exists y in big Y such that g of y is equal to z. Yeah? So pick any z you want, you can find a y so that you get that z out. Cool. Okay. Since f is surjective, there exists an x in big X such that f of x is equal to y. You agree with that? Where this y is the same y from before, from the line before, yeah? Okay. Hence, there exists x in X such that g of f of x, well, remember, this is just g of f of little x, which is g of y, which is z. So g composed with f is surjective. Perhaps I am not stating a small step right there where I say, like, since z was arbitrary, this is surjective. But I guess leaving that implicit, hey, look, we started with an arbitrary element of the codomain, and we constructed an element of the domain, or if we didn't deliberately construct it, we at least showed the existence of an element of the domain that gets mapped to that desired element of the codomain. Pick any element of the codomain, there is some element that hits it. Could be more than one. We can definitely at least pick one. Okay, so let's go a little further. Let's see if we can build up from here a little bit. Okay. What about this? Corollary. If f from x to y and g from y to z are bijective, so is g composed with f. I would say that that's a pretty straightforward corollary in the sense that we've just shown that, hey, if I jump back over to this little screen right here, we've just shown that if f and g are both injective, then so is the composition. And if f and g are both surjective, then so is the composition. Bijective functions are just both injective and surjective, right? So both at once, both at once. Cool, okay. That's not too bad. But now, let's prove some of those observations we made a little bit earlier. That is, well, perhaps let me motivate it really quick. Let's consider an example first. So, define, well, let's call it G, how about? Or F. From the natural numbers to the real numbers by f of n is equal to n squared. Since all natural numbers are positive, f is injective, right? Now, maybe that's some kind of weird reasoning, but I'm basically just going, hey, look, you guys know the only things that get sent to the same thing by the squaring function are a number and its negative, right? You know, the graph of a quadratic looks like this, yeah? So you pick any value, and it's only this thing, and it's negative, right? Okay, cool. So if you're good with that, then you can buy that this is injective. All right. Now, consider the function g from R to R by g of x is equal to x squared. It seems like the same function. Is this function injective? Yes, you're right. This function is not injective since g of minus 1, well, that's 1, and that's the same as g of 1. Yeah? Okay. If you wanted to be more pithy about it, you could say g of minus x is equal to, well, x squared, which is also equal to g of x. Yeah? So in fact, there's quite a lot of values that get sent to the same thing. There's 2 per. Oh, man. Except with the notable exception of 0. One of the only ones where everything is nice. Okay. However, g of f of n, well, this is just equal to g of n squared, which is n squared squared. This is n to the 4th, is injective since g composed with f has n, the naturals, as its domain. Yeah? Do you agree with this? Yeah? And I will say, and all values output by f are positive. Yeah? So you don't run into this whole issue right there. So I guess what I'm trying to highlight is, look, the same exact function can be injective or not injective. Well, not exactly the same exact function, but I'm trying to say, like, doing the same exact thing can be either injective or not injective depending on the domains and codomains. Functions are not just like a tool that says, like, do a thing to a thing, right? They have specific domains and codomains with them, yeah? Even though f and g agree at every single natural number, they are not the same function. G is defined on a larger set. They have the same codomain, but different domains. So doing the exact same thing, different function if it's on a different set. Does that make sense? Okay, cool. And that can change whether or not it's injective. And even more confusingly, perhaps, is that you can have the composition of an injective function with a non-injective function, and you can still have that be injective. Huh. Wild. Yeah? Okay, so you can't say perhaps quite as much in this case, but you can still say something. That is, like we started out by noting, we have the following nice little fact. Okay. So we have this one, theorem. This is 5.16. Let f from big X to big Y and g from big Y to big Z be functions, then if g composed with f, which remember is a function from x to z, if this guy is injective, I'll say it this way. If that is injective, then so too is F. That is, if the composition is injective, then the inside function also has to be injective. Yeah? Okay. Proof. There's a couple of different ways we could prove this. We'll go through by doing, what would you do? Contrapositive. Okay, so you're going, look, G composed with F, injective, implies F injective. So you're going to say F not injective implies G composed with F not injective. Reasonable. Let's do that. Okay, cool. So, to be clear, we should start off by saying something like, we prove the contrapositive. Suppose F is not injective. Then there exist x1, x2 in X with x1 not equal to x2 such that f of x1 is equal to f of x2. Do you agree with this? That's what it would mean to be not injective. After all, if a function is not injective, there should be at least some witness to that, right? Some example showing it. If you couldn't find any such x1 and x2, then it would be injective. Yeah? Okay. So, G of f of x1 would also be equal to G of f of x2 for x1, or I'll say with even x1 not equal to x2, and G composed with f is not injective as well. Do you see why these two are equal? It's because these are equal. You're doing the same thing on both sides. You're just applying G to both sides. Applying G to a thing, applying G to the same thing, you get the same thing. Okay. That is, we've produced a value x1 so that if I plug it into f composed with G composed with f, however you want to pronounce that, we get the same thing. Cool? Okay, that makes some sense. Pretty nice. Now, this will give us some kind of nice consequences. We'll try to prove the same sort of business about surjectivity momentarily. You feeling all right about that proof? Nods? Okay. It's a Monday morning. Okay. Here is a theorem about the opposite result. So let's let f from x to y and g from, yet again, y to, can you guess it, z, be functions. If g composed with f, which is a function from x to z, is surjective, then so too is, can you guess which one? G. Proof. How would you like to go about proving this one? Okay, right on, right on. Does everyone see what the intuition of this one is? It's the same picture we drew at the beginning. That is, if you follow arrows, you can hit everything on the last column, Well, then there must have been an arrow from the second column to the last column for everything, right? Makes some sense? Yeah. Okay. So we could do the same exact kind of approach. I heard someone say that. Let's try it. Okay. We could try proving the contrapositive. We could say, suppose G is not surjective. Then there exists Z in big Z such that G of Y is not equal to Z for all little y and big Y. Agree with this? That is, nothing ever hits that one. Okay. So, certainly, G of f of x is not equal to Z for all x in big X, since f of x is in Y, do you agree with this? That is, if there is no y such that G of y is equal to Z, then there is certainly no x such that G of f of x is equal to Z, since f of x is just equal to some y, right? Since the codomain of f is y. F sends x's to y's. So if there was such an x, then G would send that y to Z. If there was such an x that let you get there, that would imply the existence of such a y. To be clear, i.e., if G of f of x equals Z for some x in X, then there exists y in Y such that G of y is equal to Z, namely, y is equal to that value f of x. And we have assumed that that is not the case, that there is no y that gets gets sent to that Z. Okay, does that make some sense? We said, hey, G not surjective, then G composed with F. This composition right here, put F inside of G, also not surjective. Contrapositive, composition surjective, implies G surjective, right? Cool. Okay. Now, what about inverses? Isn't that kind of what we're building to? Don't we want to talk about when we can turn arrows around in some sort of a reasonable way? Yes, exactly right. So, to get to inverses, we should probably describe what they are. Let's throw a little definition up here. All right. If f from x to y is a function, the inverse of f is the relation I'll write it this way. Let's say it's the relation G from y to x defined by Well, G is equal to the set of y x's such that x, y is in F. It just flip it around, yeah? Notice under this definition, every function has an inverse. It just may not be itself a function, right? That is, the inverse of a function is a relation, and those particular cases where the relation is a function are the ones that we usually talk about. And in fact, notice, you don't even need F to be a function. We could just talk about the inverse of a relation. Yeah? Just flip everything around. Cool. All right. So that's possible. All right. Now, maybe put that as a small note. Let me just say that specifically. Note. Every function under this definition has an inverse. It just might not be a function itself. So a lot of people reserve the word inverse for the case where we have, actually we get like a function back, yeah? Here we're proceeding without that. That's a convention of your textbook that, you know, there are reasons for it and against it. It is nice to be able to talk about an inverse by itself. That is to talk about this flipping operation without needing to, you know, specify whether or not the thing is a function. After all, they're two separate things, right? You can flip without getting a function, and you can flip and get a function. So keeping them separate makes some things cleaner to state. On the other hand, it perhaps disagrees with some of your intuition about what's going on that you've developed in previous classes where they use inverse to specifically mean another function. So, you know, 6 of one, half a dozen the other, right? Quick example, just to make this super clear. Let's let f from the reals to the reals be the function f of x is x squared. Then the inverse of f is the relation, not function, g, defined by g, well, it's just the set of ordered pairs of the form x squared x such that x is a real number. Yeah? Oh, okay. Cool. Reasonable? This whole business kind of makes some sense. Nice. Okay, so here's the question that we have to ask. Or maybe even I'll put some notation. Let me say this. Let's say a function is invertible if its inverse is also a function. This is maybe even more confusion-inducing in the sense that we'll talk about taking the inverse of something, but then be like, but it's not invertible, which sort of seems wrong since invertible seems to suggest, can you take an inverse? But instead, the able part of it is meaning whether or not you get a function, right? Can you take the inverse and get a function? If you can, invertible, I suppose. So here's the question. When is a function invertible? I heard the answer. Someone already knows. Someone has seen this before, I imagine. A function is invertible when it is injective and surjective. We should probably show this in some way. So here's the question. When is a function invertible? And I believe you all already know the answer, but we'll actually get there and rigorously prove it next time, since it is 10:59. So I'll see you around, and yeah, have a great day.